Now, I'd like to tell you a story, and this story is really the most interesting question that human beings can ask. And that question is, where did we come from? Because unless you imagine that a big hand came from the sky and put us on the earth, the logic is, and the logic is ruthless, we self-assembled. Now that seems very difficult to understand. How human beings possibly self-assemble? But that's what they did. Now what I want to do is to tell the story of not just the self-assembly of human beings, but the self-assembly of everything in the natural world. And that means the whole universe. Now, if we self-assembled and everything else self-assembled, there must be an awful lot of evidence all around us, all the time. So why can't we see it? Well, we can, but we're hardwired to miss it. We always miss the obvious. So let's go back, right back to the beginning of time, when there's just hydrogen atoms. Because we all know that everything's made of atoms. So there must be something in the atom which causes the self-assembly. Now it just so happens about 2 weeks ago, for the first time human beings glimpsed the Higgs boson. And I know a lot of you will be wondering, what was all that fuss about? And why were people so happy to find the Higgs boson? Who cares? Why build a Large Hadron Collider? Spend all that money to find a little particle? Well, as it turns out, that was the last piece of a jigsaw. And that jigsaw is now complete. The jigsaw is called the Standard Model. And the Standard Model simply tells us how an atom can exist. So it's got to be something to do with the atom. The self-assembly must be there in hydrogen. Now, as you all know, hydrogen is simply something which you imagine to be like this, one thing that's plus and something that's minus. How can that cause the self-assembly of everything? Well, the first thing we've got to do is change our mind about matter. Matter is very, very strange. It's not intuitive. Now, this is going to show you how we miss the obvious all the time. So, if I put things on this table, this is going to be my table of fantasy. It's not real. So I'm going to put my imagined atom on this table. Because we see pictures of atoms like this all the time in books, with little balls, that's the idea we get. But nothing could be further from the truth. There are no little balls. Now, it's very easy to be tricked by matter. When I look at something like that, and I can't put my hand through it, I get the idea, if it was made of little balls, it would be something like this, solid. But that can't be true. Now, here's why. The next time you pick up something solid and look through it like this, there's something wrong. I can see everything on the other side, but I can't put my hand through it. How can that possibly be? Matter must be something very different. Now, this is matter too. And I see absolutely nothing. But it's real. So I've got to change my idea about reality. This is strong enough to lift an aircraft, a 747, up into the air. But I see absolutely nothing. So I need to change my mind completely about matter. There are no little balls. There is nothing to see. Matter really is an illusion created by the light which comes out of matter. So let's tell the true story. to self-assemble from a hydrogen atom everything in the universe, elements. If I go back to just hydrogen, there's no elements, there's no oxygen, there's no iron, nothing else, just hydrogen. No stars, no planets, no molecules, nothing, just hydrogen, one plus and one minus. Now, let's tell the story of the Standard Model, because if that's where we come from, everything must be a direct cause of this, the Standard Model of an atom, what an atom really is. So, once we've put out of our head any notion of little balls or things, what is it? Well, because we are the net result of atoms, this is all an illusion. It's just something which my brain can hang on to. What I want to do is to take you into another world, a world of a very different reality, the quantum world. Now, about 3 weeks ago, a little boy called Benjamin asked me, what does quantum mean? You've all heard of quantum mechanics, quantum physics. What does it mean? Is it all just something we make up? Absolutely not, otherwise you wouldn't be able to see me. Now, quantum means an amount. Everything, it turns out, comes in small amounts. So, the next time you're looking at the ocean, or sunshine streaming through the window, that all comes in little packets, and every little packet is absolutely perfect. If you wanted to search for perfection, it would be the fact that all electrons are exactly the same, 100% perfection. But what is an electron if it's not a little ball? Well, I'm going to call them quantum entities, these little ethereal regions of space in which something is different. Now, if I want to make an atom, I need some parts, some bits to make it from. I need some forces which interact with the parts. And I need some force carriers, some other little quantum entities which are going to carry those forces around the universe. And as you will see, this jigsaw, it all fits together very, very nicely. Now, we'll start with the parts. I've got 12 parts. We call them fermions. Now, remember I said everything comes in little packets. Everything is quantized. The parts are quantized. The forces, the energy, the force carriers, and even their properties, something we call spin, its angular momentum, how it moves, actually comes in little packages. Now, there's a clue here as to what these quantum entities actually are. This force carrier here, the photon, the one that carries electromagnetic energy, the light coming through the window. Well, you all know this equation, E equals mc squared. Well, let's look at what that's really telling you. It's telling you that energy and matter are equal. It's the same thing. That seems very strange. I don't really see the light coming through the window as something like this. Well, that's why I need different little parts. But it means I can change them from one thing into another. Now let's go back to my parts here and see if we can slowly build an atom, something from which the self-assembly can start. Now, the first little bits we're going to call quarks. It's a wonderful name. And quarks are very special because they interact with something called the strong force. Now, you're used to dealing with forces because there's visible forces, forces that you are aware of every day. Gravity, electromagnetism. They're only two visible forces. But there must be something much stronger than electromagnetism, or my atom would fly apart. Now you all know that like poles of a magnet repel. There's a repulsive force. Well, if I look at this atom here, in the middle, if I've got two positive charges, that would just fly apart. There must be something stronger that's holding them together. Now, because the quarks feel the strong force, it can bind them together, and I can make a nucleus against that repulsive force of electromagnetism. But I can see the smart people out there thinking, well, there's a problem with that, because why doesn't the strong force just bind everything together? Well, here's the clever bit. It only works over a very short distance. Very, very short. And some other of my parts, which we call fermions, leptons, don't feel the strong force. So the electron, which is a lepton, doesn't spiral down into the nucleus because it simply doesn't interact with the strong nuclear force. So now I'm beginning to see how I can have something which is stable and doesn't just disappear into itself. Now, this is where the Higgs boson comes in. If atoms are not made of little balls like that, how can they have mass? Well, you're all very aware of what happens to mass when it's in a gravitational field. But if I take something away out into space, a long way away from a gravitational field, and I push on something like this, we would both move away, but there would be a resistance. We wouldn't both shoot away at the speed of light. But resistance to what? There's no little balls. Now, imagine a field everywhere. The Higgs field, a field which all particles are going to interact with. Well, that starts to solve the problem. In fact, some particles don't interact with it at the photon, so it can move through the field at the speed of light. Now, when I talk about interact with, imagine walking through a room with people. If you don't know anybody, you just walk through the room. You don't slow down, you just continue on your journey. But if you know somebody, you might stop and talk to them. Now that gives the illusion that you're heavier. It's making you slow down. It's not. It's the interaction which is taking place, which is causing you to slow down. Now, if we go back to this part here, my fermions, my parts of matter, actually come in 3 different generations. Each one is just the same, but it has more mass. Now, because it's not a little ball, that doesn't mean it's a big ball, this ball is bigger than this ball, it just means it interacts with the Higgs field more. Now, you all recognize this, the electron. There it is. It interacts with the electromagnetic force, and it has a charge, we say, of -1. We'll talk more about that later. Each one of these fermions has a partner. The partner to the electron is the neutrino. The neutrino has no mass. Now that just means it doesn't interact with the Higgs field. In fact, it does have a tiny, tiny bit of mass, but not enough to slow it down. It doesn't interact with the electromagnetic force. It doesn't interact with the strong force. And because it doesn't interact, the neutrino will pass straight through the Earth as if it was not there. It doesn't even notice. The whole Earth is there. Because matter is not like this. It's much more something like this. Now, if that was a proton, not a solid ball like this, my electron would be maybe a kilometre over here or over here, a kilometre. And that means a cubic kilometre of empty space. That's why you can see me now. It's all empty space with little bits of fermions and interactions taking place in that empty space. Now that's a theme we're going to see again in the universe. Lots and lots of empty space. So I can put my idea of matter, of solid things, being balls which are all together, on my table over here of fantasy, because everything, even the earth, is all really a lot of empty space. If I took all the fermions that make the whole earth, everything, all the oceans, all the mountains, and all the hot magma inside the earth, that seems a lot of stuff. But if I put it together, it would be about this big. So that's how much matter, that's how much stuff I need to make the whole earth. It really is empty space. Now, we still haven't made an atom, so let's get back to the process of trying to make an atom. Now, the electron, which does interact with electromagnetic force, but I need something to balance it, and you'll see why balancing it is so important later. If I go up here, I've got my quarks. Each one has a partner. The two with the smallest mass, the up and the down, they two interact with the electromagnetic force. The up quark, I've represented here as blue, is plus 2/3. The down quark, minus 1/3. Now these bits of matter here, we don't need them to make the standard model. There's many other kinds of matter in the universe, but they're not stable. And there's also lots of very strange other places which we don't really have any idea of how it all works. You see, we only know about 4% of the matter in the universe. Everything else still has to be discovered. But I need 4% to make me and you and the stars and everything else in the natural world. So these bits of matter here, we're going to leave those to the rest of the universe. I just need these bits here. Now you might be wondering why I need a neutrino, which doesn't interact with anything. But you'll see, without that, I can't have elements. And I need elements to self-assemble other things. Now, let's see if we can make a proton. Something which takes up some space. And inside that proton, there would be 3 quarks. And I must have 3. I'll show you why later. Now, I want to get an electromagnetic charge of +1 to balance -1. But 1 what? Well, this is something we call the fine structure constant. And again, it's quantized. It's an exact amount. So it's one of those, and if I balance it exactly with one of those, it cancels itself out. And if it didn't, you and I and everything else would disappear. We'll see why when we come to visible forces later. So let's try and make a proton. If I use one up quark and another up quark, I get 4/3 electromagnetic charge. One down quark, you see, minus 1/3, I get +1. So I've got a proton made of 3 quarks, an electron, which is the same as a quark. It's a basic particle of matter. So here, I've got a hydrogen atom, but I haven't got any elements. To make elements, anything bigger than that, I need a neutron. Now, let's see how we can build a neutron using the same parts. If I use up and down quarks, one down quark, -1/3, another down quark, -1/3, and one up quark, well, that's -2/3 plus 2/3, I get an overall charge of 0. And that's going to be very, very important later. Now, I've got my building blocks. The hydrogen atom, from which everything comes, doesn't have a neutron. Well, it can have a neutron in some special cases, and it makes deuterium and tritium. We'll need those later. But if I want an atom like this, which has neutrons in the middle, there's another problem. You see, I've squashed together these two protons. I've got plus and plus trying to go together, and they don't want to go together. I need the strong force. Remember this one? It acts over a very, very short distance, but I don't have enough of it if I've just got two protons. Remember, they are interacting with the strong force and the electromagnetic force. So if I put two neutrons, which are zero, I've got some more strong force without having any more electromagnetic force. Now, if these patterns, which are all around me, are all a direct consequence of this, then I should be able to explain everything, even me, in terms of this. So what patterns are all around me? What am I going to see? Well, I'm going to look for patterns of symmetry, asymmetry, ratio, periodicity, colour, and shapes. Now we take all those for granted because we're programmed to. But if those patterns are all consequences of this, they're telling me a story. So I'm going to think again about natural patterns. Patterns like this is telling me a story. A pattern like this is telling me a story. I'm going to think of symmetry. This is a star which is beginning to explode. And the symmetry tells me a story about this. Patterns like this. Now, you've all seen pictures like this. This is the biggest thing that we know. It's a galaxy. And there's the same pattern. Well, isn't that telling you something? Patterns have meaning. But it's not the meaning we give to them. It's the meaning that we find, and we find it here. That's very important, because it means it's not people's ideas. It's something else, something much more intelligent, hopefully. Patterns like this. Now these are the rings of Saturn. The patterns must have self-assembled from this. That's the story I really want to tell you. Because if you can read these patterns, you can learn so much about that story of self-assembly. Now, I've seen these patterns somewhere before, in this graph here. Now this, would you believe, is a graph of insect populations. And it's simply a graph which shows how much order is in that population graphed against the birth rate. Now what you can see in these rings of Saturn, there's parts where there's nothing. And that means that something is cancelling itself out. We're going to see that theme a lot in the story. Remember, plus and minus, they must cancel themselves out. And let's see why we can put this down to what we see here. Remember, I've got to explain everything in the natural world just using these tools. Now, we've made our atom using these forces, using these parts, and using these bits which actually carry the forces. The force carriers, we call them bosons. There's the gluon. The gluon carries the strong force. The W and Z particles. Now the W and Z particles carry the weak force. Now I need the weak force to make a neutron. Let's see why. Let's go back over here Here's my neutron. You can see I've got one quark which is changed here. Now, a proton is stable. That means once it exists, it continues to exist. The electron is stable. That's the same. These are the only two stable bits of matter that we know about. There are hundreds and hundreds of bits of matter, but they all degenerate into something. Some of them lasting 10 to the minus 21 second or something like that. And the neutron, which is also unstable, that means it can't exist by itself. It's stable for about 15 minutes, no more, and then it changes into a proton. And it does that by releasing one electron and one neutrino. So the neutrino here has to do with making this neutron. Now, the neutrino, because it doesn't interact with anything except the weak force, is very, very hard to find. It passes straight through the Earth just like the Earth is not there. So how do we know it's there? Well, when this electron comes out of the neutron, you can see there was something here making it travel in a particular fashion. And we guessed it was there, but we didn't find it until somebody had a brilliant idea. How could you possibly find something that's not going to interact with you or me or any instruments that you build? Well, this process also goes backwards. I can put these two back into here and change a proton into a neutron. And that means I'm going to change the element. Now, if I take the element chlorine, chlorine 37, that will change. If I change just one proton back into a neutron, it will change into another element. So if I have a lot of chlorine, and this is how the experiment was done, somebody had the brilliant idea of putting a lot of chlorine inside a mountain, and then you measure how much of that chlorine changes into another atom. That atom is argon, argon 37. And that tells you that this process is actually happening. So I can infer from that exactly what I want to happen. For the whole model to remain intact, to remain stable. So let's see what we've got now. We've got a proton, electron, a neutron, and I can make an atom. It all must balance. Now, there's another problem with fermions. You can't have two in the same atom doing the same thing. So they have to spin round. But look, if I've got one spinning in this direction and one spinning in this direction, I don't break the rule. They're not human rules. These are the rules of the universe. This is how it must work. So here I've got a helium atom. I've got enough strong force to keep this together, and I've balanced plus and minus. And that is going to be really important. Now, remember I said there's going to be lots of evidence in the shape of patterns which are all around us. I've got my visible forces here. This is what we experience. So let's have a look at our first pattern and see the problem with having forces. Now, you all know the Earth is a sphere. Remember, patterns have meaning? That's telling you a story. The Earth must have self-assembled, and if it self-assembles into this pattern, it means the force doesn't have poles. Now, we're going to look at these two forces here. This one, electromagnetism. It's got two poles, which are doing, they can attract and repel at the same time. So if I look at my model here, I start to see something very, very special happening. These are attracting and repelling at the same time. That's going to be very important when I make molecules. Now, this is something which is really, really important. I want you to look at the strength of the forces, this ratio. 10 to the power of 40. Gravity is very, very, very small. I'm going this way. Electromagnetism is 10 and 40 zeros stronger than gravity. 40 zeros stronger than gravity. Gravity is very, very, very weak. Much too weak to have anything to do with particles like this. Let's just show you how weak gravity is. Gravity is inside all the atoms that make the Earth, all the oceans, all the land, all the hot magma inside. That's an awful lot of atoms. There's more atoms in my hand than every grain of sand in every desert on the Earth. That's a lot. So imagine if I could count all the atoms in the Earth. Now, let's see how much interaction that has with a piece of paper. More atoms in there than every leaf on every tree on the whole Earth. And if I just drop it, all those atoms in the Earth, just manage to pull it down. Now, it must be like that. If it's not like that, everything changes. Let's go back to my ratio here. Gravity. Very, 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 very weak. So weak it can't possibly have anything to do with this. But it can make big things, like the Earth. I need a weak force, because when I make something big, if that force is strong, well then I get too much force, and it disappears. To answer that, to show you how that works, think of a force, electromagnetism, which is 10 and 40 zeros stronger than gravity. 40 zeros stronger than gravity. Now that means if I was pulled down to the Earth by this force, and not this one, I would be heavier than all the stars in a galaxy. It doesn't work. So what would happen? If this was the force which was sticking the big things together, everything would disappear. Now, remember, I've got plus and minus. I want you to see them as balancing each other. The word attraction, I've got to be very careful with it. They're really cancelling themselves out. So that all the force which is making all the small things, not the big things like planets and moons, is made by something that cancels itself out. And if it didn't do that, the Earth would collapse, disappear into a dot. A dot. Well, very just the same as a black hole. If I get too much gravity, which is so small, everything disappears. Well, imagine trying to make something with a force which is 10 to the 40 times stronger. You can't do it. Everything really would disappear. So it's very, very clever to make it from a force which cancels itself out. Now, when you see lightning or any chemical reaction, that's a tiny, tiny bit of asymmetry in that force. And I do mean a tiny, tiny bit, but it's that asymmetry which is really going to make things. It's going to self-assemble things. We're going to need that later. So I've got a force here for making big things, forces here for making atoms, and a force here which is going to stick atoms together to self-assemble smaller things, but bigger than atoms. The helium atom is absolutely useless because it's well balanced. There's no asymmetry. This one balances this one balances this one. Nothing would happen if the universe was made of atoms like this. There would be no self-assembly, none whatsoever. So all we've managed to do today is to get an atom from which we can start our self-assembly. process, but an atom which can simply exist and make matter which is like this, or like this, or anything else that you can imagine. Now, the second video we're going to make is the self-assembly which starts when I unbalance this, when I give this some asymmetry. And that's really important because it means that things are happening by themselves. Now, if I go back to when I've just got hydrogen in the universe and nothing else, there must be something which is going to start to make those hydrogen atoms clump together. And what force am I going to use? Well, I'm going to use this weak force, which doesn't have poles. That's why it always makes spheres. So when you show children pictures like this, what they don't notice is that they're all the same pattern, a pattern which is telling me a story, but it's made by gravity. Now, the smart children will say, well, the Earth has a magnetic field as well. It does. But remember, if the Earth was held together by electromagnetism, it's so strong it would disappear. Now, we're going to use gravity later in another lecture to assemble the elements. Now, because gravity can only make spheres, when I look out into space, I do see spheres, but I also see disks around the spheres like this. Well, that's just like the solar system. So I'm beginning to see patterns of self-assembly in the solar system. And you have to remember, you're a product of the solar system. Now, I need to find some order and structure in the solar system which is going to allow it to exist for long enough for evolution to take place, because there will be patterns in living things which give away how it's working. Now, I'm going to do that in lecture number 4. Now, that's the end of what we wanted to do today. So I hope that we've changed your mind about matter. It's nothing to do with what people could ever have possibly imagined. And the word imagination is going to be very important later, because we're the only living species which has an imagination. There will be patterns that show up in our fantasies, which are universal truths that show up in every different culture on the earth. And that will be another giveaway of what's really happening. Well, that's the end of the lecture today. Next time, we're going to start the self-assembly of molecules. Bye for now.